your password isn't encrypted. Depending on who built the site you are using, that's either the best possible news or a serious problem. Which one is it comes down to whether the developer knew the difference between hashing and encryption, and the surprising number don't. Scramble the data, save result. Seems close enough, right? Which is technically correct in the same way calling a submarine a boat that doesn't like air is correct. Hashing and encryption solve completely different problems, and if you mix them up in a real system, you probably introduced a serious security hole. Let's clear this up. Hashing takes an input like a password or a file and runs it through a mathematical function that produces a fixed length output. That output is called a hash or a digest. But the key idea is that hashing is a one-way function. You cannot reverse the function to get the original input back. And before you think this is a magic bullet, you can guess inputs, hash them, and compare the results. That's how brute force attacks work. So if you run cucumber32, which is a creative but not a strong password, through a 256 algorithm, you get a 64 character string every time. Same input gives same hash. So how are these hashes, not hash brownies, used for passwords? Well, when you register on a website that actually cares about security, your password gets hashed, and only the hash is stored. That means that when you log in, the system hashes what you've typed and compares the two hashes. A match means you get logged in. Easy. As you've probably figured out, the actual password is never stored. And this is exactly why a well-built website cannot email you your password. They don't have it, they can only reset it. If a site emails you your password in plain text, that's a huge red flag, and it should instantly tell you that they don't care about security, and you should carefully examine what data you are entrusting them with. So good then. Now that we got hashing, we should talk about encryption. Well, encryption is different. Encryption is a reversible process. You take the data, apply a key, and turn it into ciphertext, scrambled data. With the right key, you can reverse the process and get the original back. This is the whole point. And there are two types of encryption. You have symmetric, where one key is used to encrypt and decrypt. AES is a standard here. And you have asymmetric encryption, where you have two keys, a public key to encrypt and a private key to decrypt. TLS, for example, uses asymmetric encryption to exchange a session key and then switches to a symmetric encryption for actual data transfer. But, and this is a big one, and yes, this would be a great opportunity to make a joke, but please stop it and be serious. Encryption is only as secure as your key management. If an attacker gets both the encrypted data and the key, the encryption doesn't protect you anymore. And if you've watched my recent videos, you know that in real system, an unfortunately common mistake is storing the key right next to the encrypted data. And that's basically nothing. Zero security, pointless. The easiest way to remember it is like this. If you never want to see the original data again, hash it. And if you do need it back, and you've hashed it, well, now that's a personal growth moment. If you need the original back, encrypt it. That's exactly why we hash password. There is no point for a website owner to see your password. He only needs to verify it. If we think about the bigger picture, hashing is about integrity and verification, and encryption is about confidentiality. Going further, things like digital signatures are about authentication, and they combine both to prove exactly who sent the message and ensure the sender cannot deny they did it. Different tools, different goals. But they frequently team up to build complete secure systems. So can't we just crack a hash? Well, depending on implementation, yes, because hashing is one way, but it's deterministic. Same input, same output. This is how rainbow tables that contain common passwords and their hashes appeared. If your hash is in that table, the respective attacker has your password. And obviously we're talking about huge tables. And just how salting gives food a better flavor, it also helps us beef up our security. A salt is a random value added to the password before hashing. So, translucent kangaroo 22 becomes something like translucent kangaroo 22 plus a random string. Now even an identical password produce different hashes and the rainbow tables stop working. To keep it gastronomical, we even have the pepper concept, where a secret value is stored separately from the database. So even if the database does leak, the attacker still doesn't have everything needed. Modern password hashing algorithms like bcrypt and Argon2 handle salting automatically and are deliberately slow, because speed is the enemy when it comes to passwords. Modern GPUs can try billions of SHA-256 guesses per second, and we don't like that because that would mean your password would be cracked with little to no effort. Some real-world examples so things can land clearly. The password manager encrypts data because you need it back. Every Git commit has a hash. Change anything and the entire chain breaks. And since I've made a video recently about it, HTTPS uses asymmetric encryption to securely exchange a key, then symmetric encryption for fast data transfer. And because you might have heard about it, encoding. Encoding is not encryption. Base64 and URL encoding don't protect data. They just represent it differently, and anyone can reverse them instantly. So to wrap up, hashing is one way, encryption is reversible for when you need the data back, and encoding is not security at all. If this video was useful, subscribe to the channel. Part of what we do here is breaking down tech concepts like this without random fluff. Maybe some salt and pepper here and there, but nothing more. I'll see you in the next one.